spring pendulum, we have, in the spring pendulum, we have an object that's literally oscillating back and forth, back and forth. So it's this way, it's stretching, it's going all the way out here, and it's coming back, and it's just literally going back and forth, back and forth, back and forth, right? We know what a period is. It's a time to complete one cycle. So if it starts here, the time it takes to get back to that cycle, that's a period. The frequency is the number of cycles that it makes in per unit time. Nothing's changed there. Displacement, we say when it's at rest, when it's not squashing the spring or stretching the spring, when it's neither squashed nor stretching the spring, we call that equilibrium, right? And equilibrium is known as x equals 0. That's the equilibrium point. Equilibrium point, x equals 0. The displacement is the distance that the object is traveling away from the equilibrium point. When that distance is at its maximum amount, we call that an amplitude. So let's go back. So when we're at our stretching the spring to the maximum amount, we're going to call that all the way in the positive direction. We're going to say that that's the A, or amplitude. When it's all the way squashing the spring, we're calling that the negative amplitude. So it's the furthest it can compress the spring. When the spring is neither stretched nor compressed, we call that equilibrium, x equals 0, right? We always measure from that point. They throw this little equation out here. This is known as Hooke's law. Kind of an important little term, which means that the more you stretch a spring, the greater the force it takes to stretch that spring. This K value, I don't know if you've seen this before, but K is known as a spring constant. And every spring has a certain constant associated with it. And it's how I tell my students most of the time, it's just the springiness that's associated with the spring. Sometimes springs are very difficult to stretch. That would have a very high K value. Sometimes springs are very easy to stretch. That would have a low K value. And there's also the other types of springs that are very difficult to compress, high K value. If they're easy to compress, low K value. So it's a value depending upon the spring that you're using. We have a quick Hooke's law problem here. A spring whose spring constant, so that's K, right? 20 equals Newton meters, let's write the givens, is stretched, so that's X, that's the distance it's stretched, 0.2 from meters from equilibrium. What is the magnitude of the force? And remember, force are in newtons. So we can use Hooke's law, F equals Kx, and plug in our values, and that force is 4 newtons. Some of you have a sharp eye will probably say, hey, wait a minute, aren't you missing a negative sign? Didn't they tell us that there was a negative sign here? Well, that's true. To be honest, the negative sign is not real important. What it means is that springs have a restorative force. If you stretch them, they're going to want to compress. If you compress them, they're going to want to stretch. So the negative sign isn't critically important whether you use it or not. Let's move on. Let's look at the situation when the spring is all the way compressed. You know, when it's compressed all the way like that, you know that the displacement is all the way at the negative amplitude, right? It's this direction. So we're calling to the left negative, and it's all the way as far as it can, that's negative. You're squashing that spring. You have a tremendous force, a maximum force, and that force wants to shoot that spring over to the right. So the force is in the positive direction. The acceleration is in the positive direction. When it's already squashed like this, it's going to be taking off and getting faster and faster until it reaches that equilibrium point. So the acceleration is in the positive direction. Now, if this is going back and forth, If it's going negative, negative, negative until it compresses the spring, it has to go to 0 before it starts going positive, so the velocity is 0. Now we're at the equilibrium point, but traveling to the right. The displacement is 0 because we're at the equilibrium point. The force on the spring is 0, right? And why is the force 0? Well, think about it. We're not compressing the spring any longer, and we haven't yet stretched the spring. It's sort of in that neutral position, so there's no force on it. And going back to Newton's second law, F equals ma, if there's no force, there's no acceleration. Acceleration is 0. The velocity is positive because we're going to the right and is at a maximum, right? It's as fast as it's going to get when we're at the equilibrium point. Now we're all the way to the right, and we're stretching that spring. So you know we have a maximum force, and that force is now pointing to the left. It's negative. The displacement is at the positive amplitude, right? It's all the way to the right as far as it can go. Velocity, once again, is 0 because it's going from a positive to a negative direction, so we have to cross that 0 point. And the acceleration is maximum, but now the acceleration is going in a negative direction. Once again, we returned back to the equilibrium, but we're heading this way. The displacement obviously is 0 because we're at equilibrium. We're not stretching or compressing the spring anymore, so the force on the spring is 0. If there's no force, there's no acceleration, and the velocity is at its maximum value, but headed in the negative direction. You might want to pause this video and think about this, or go back on it, go back over these few slides and think about that a little bit more. If we were to take this oscillating mass spring and put it vertically instead of horizontally going back and forth, now it's going up and down. It's the same situation. We just changed the equilibrium point by hanging a mass on it. That mass is going to be pulling the spring down a little bit further to an equilibrium, but all the conditions that we just discussed hold true. At which location is the magnitude of the force of the mass in a mass spring system a maximum? Well, think about it. When you squash the spring all the way down, that's negative A. That's going to be a tremendous amount of force on that spring. And when you stretch that spring all the way, that's at positive A. That's going to be a tremendous amount of stress. So our answer should be, in case you're looking here, D. Now they want to know at which location is the magnitude of the force on the mass in a mass spring system a minimum. So where is there a minimum force? Well, you want it where the spring is not compressed and where it's not stretched. And that would be the equilibrium point.